welcome everybody once again to our first showdown of 2022. We're really excited about today's. We're introducing 3 new materials from Lehvoss, and that's why we have our colleague Tiago Medeiros, joining us today from Lehvoss. He's a materials engineer from Lehvoss. We'll be talking about what these 3 materials are, how can you use them, how can you print with them, and the method. I also got the safety glasses, so I always know that that's, it means that it's going to be fun. We're going to be breaking some of them, testing the structural integrity of them against our, well-known rig over here. I have one of them printing. It's actually the PET reinforced carbon fiber. We'll talk about the specific of that one as well. But yeah, all in all, it's the 3 new materials from Lehvoss. And the way that we'll structure is going to be as follows. We'll talk about the technical specifications of the materials. We'll talk about what they are. Tiago will give us then a quick rundown of the specifics of them too. And once we're done with that, we'll come into the jig. We'll break them essentially. If I can switch over my view, in case you guys haven't joined us before. But what we are going to do is just a strength test here, pulling the samples apart. We have 2 samples of each of the materials. And then we'll collect the data, see how each of them work out. Overall, we have 1 nylon, so the 9825 nylon. We have a high temperature carbon fiber, 9821, and a PET carbon fiber, 9780. Those are the samples that we will be talking about today. And a few of the printed parts that we have already tested out here on the method. So how do you actually print with them? What are the best applications? And yeah, just generally speaking, why would you use them with the method, and what are the implications of using it with the method versus other systems? So with that, I'll get started. And then I don't know, Tiago, if you want to jump in and introduce yourself before we get going.
Yeah, hi everyone. So first of all, Felipe, thank you very much for the invite to receiving me here. Yeah, so my name is Tiago Medeiros, and I'm materials engineer, as Felipe said, and my responsibility in Lehvoss is as a product manager for the LUVOCOM 3F line. So thank you.
Welcome. Really happy to have you. And especially, you guys will see why in a second. He's got a lot of in-depth expertise of the actual material science behind these 3 materials. So let's start at the changes in the method as a whole with the addition of these 3 new materials, right? So right now we are looking at 30 materials for the method printer. The method printer is this one that I got right here. 4 standard polymers, 6 of what I would call like high temperature polymers, 2 composites, 15 lab certified. Those are materials that are coming from a third party, just like these ones from Lehvoss. And what that means is that it's, with the lab's extruder, you can print any material from a third party, whichever one you want. However, some of them we actually, take a closer relationship with the supplier, in this case, Lehvoss, like with Tiago, and we do, dedicated testing of the materials, validation, and just essentially come up with the parameters to make it easier for you guys to print with said materials and have the best experience possible with the platform. And finally, 3 support materials, soluble supports, all of them, those are amazing. PVA, I'm sure you're familiar with, water soluble, SR30 soluble, but still requires an additional chemical agent to help with the dissolution process, and rapid rinse dedicated for ABS, but water soluble. Amazing, we've talked about that one in the past, but it's yeah, one of my favorite as of now for supports. Now, specifically talking about the new materials from Lehvoss, right? So we've got the PTG, actually not, that's a typo, it's just PET carbon fiber. Then the PAHT, which I think HT stands for high temperature.
Correct.
If I'm not mistaken. So high temperature, it's a nylon and carbon composite, right?
Correct. So we have the one unreinforced and one that's reinforced.
Correct. So the reinforced with carbon fiber, 9825. And finally, the PET carbon fiber, which is a 9780. All of which are compatible with the lab's extruder. Speaking about the printers, you can print them, the 3 of them, you can print them with a method or a method X. Both printers will reach the required temperatures, and we'll talk about the specific required temperatures in a second. But generally speaking, it depends on which support material you're using. If you're using PVA, you'll be able to print with a lower temperature in the chamber. And if you're using SR30, you will need to print at a higher temperature, usually above 70 degrees. We've had a few findings in testing those out, and we'll talk about those too when we come to them. So starting with a PAHT carbon fiber, so 98, 91. I'll try to stick to the numbers because that might be an easier way to differentiate this. But it's, as Thiago was saying, it's a nylon carbon fiber. It's super strong, Steve. I actually have one sample with me that I printed out in this machine. It's the same one that's featured in the image over there. Really strong, super stiff. All in all, like at a glance, what could you say, Thiago, this material is meant to do?
Correct. Yeah. So this is really focused in industrial applications that require a high temperature resistance. So this material, when printed in a method that has a heated chamber, then you can really have the full crystallinity of the material, and that allows it to stand up to 155 degrees Celsius. Yeah, depending, of course, on the load that you apply into it. It's easy to print material, but it's a very known in the engineering community for industrial parts.
Yeah, and it's also fairly lightweight. It feels like with the nylon substrate, it's sort of something that you can definitely use well for lightweight applications too, correct?
Correct. This is the advantage of the carbon fiber over the glass fibers. And so the density of this material, for example, is 1.25, which is a quite a good density for engineering applications.
And one question that we usually get when it comes to these composite materials is, how is the carbon applied? Because we know that there's some systems that offer a single thread of material running through the print. In this case, the carbon is evenly distributed across the filament, correct?
Correct. This is the difference. So in this case, we use short fibers. We don't use continuous fibers. We have, of course, not so strong parts when the fiber is aligned. So when you measure everything aligned, but in the other side, when you measure the properties outside of the direction of the fibers, then this material is much more resistant than a continuous carbon fiber. So when you have multi-axial loading, preferable you have a short fibers. When you have a single side loading, preferable you have a continuous fiber.
I think that's really interesting, and it's especially because we tend to think of this idea of the continuous thread being super strong, but it's only strong in a very particular specific direction. I guess like it's similar to what happens with bicycle carbon fiber layups, where it depends on how you lay up the fiber, you will get different compliance or stiffness out of the frame.
Exactly. And then in this case, of course, it's added to the Z axis. So we already have let's say a reduction because of the anisotropy of the process with the, and then with the continuous fibers, you add an extra layer of issue, and then it really brings down the resistance outside of the plane.
Okay, so I guess that depending on the application, you could say that, for instance, the more randomized distribution could be better for a more general performance of the part that comes out of every single direction, as opposed to just one particular.
Correct. Correct.
Right.
That's the biggest benefit.
That's super interesting for sure. Then next up, we have the 3FPT carbon fiber 9780. So it's essentially, it's similar in this case, the substrate is different, right? So in this case, it's going to be PET plus carbon fiber, correct?
Correct. The main fact here that we have to remember that this is not a PETG, so we don't have the glycol inside, and because we don't have the glycol, we have a high heat resistance as well. So here also we have 120 degrees C. And this is already quite high. The PET is considered, let's say, the entry-level engineering material. So it's not so performance as the polyamide high temperature. However, when it comes to chemical resistance and moisture resistance, this is actually preferable in some cases.
Right. So that's one thing that we've seen in other nylon composites, that they tend to absorb a lot of moisture. Generally speaking, the PET is a little bit more stable in that regard too, right?
Correct, exactly. So the PHT, we already worked a lot to reduce the moisture uptake in comparison to a normal PA6 or PA66. So we reduced basically 4 times, and also we reduce the speed in which the water is absorbed in the polyamide high temperature. In the PET by itself, by nature, it's already much more moisture resistant, and therefore we don't need to work so much on this.
And speaking about moisture, I think that it's a good time to also talk about the fact that these materials definitely do need to be kept at within a consistent environment. And specifically, I'll start just with I'll pause here for a second just to talk about the packaging and then the usage of the material, right? So it comes on the cardboard box, really straightforward. But then inside of the box, and I have one of them loaded, you'll get an aluminum. Is it aluminum or is it?
Correct, aluminum.
So aluminum bag. The bag is resealable, which is also really nice in the same way that generally speaking, MakerBot materials are. So it has a little zipper on the top. And you really want to keep that material inside of the bag whenever you're not printing with it, correct?
Correct. Yeah, this is very, very important. It comes also with the silica inside, and then it's important also that from time to time the users can re-dry the silica in the microwave a few seconds, and then can put back in. So then you can always keep it dry.
That's actually a good tip. I've never thought about it because we do have like the silica gels in many of the materials, but I didn't know that you could dry it up like that just in a microwave.
It's very fast. So if you take, of course, you cannot have any metal. So there is some cartridges that with metal, but if you have the one with the fabric, just like 40 seconds, all dry.
Okay, so if your microwave explodes, you can talk to Thiago.
Yeah, sure.
Okay, so next material then, and final one of this family or new introduction is the PAHT 9825, which is just nylon, correct? Without any additives.
Correct. This is just the nylon high temperature, so the polyamide high temperature. And also here, the main comparison is with the PA6, for example. And then in the PA6 also, we reduce the water absorption, so the same way as with the carbon fiber reinforced. But also, PA6, normally you have a temperature resistance at around 50 to 60. And here we can go up to 100 degrees C. So this is really the advantage of the high temperature.
Right. And also, by the way, if you guys have any specific questions, there's Alejandra on the back end collecting all of them. You can type them on the chat. We'll be answering them either as we go or at the end of the session, we'll have also a Q&A because I'm sure that we'll have quite a few things to address later on. But yeah, so generally speaking, 3 materials out of which 2 are composites, both with carbon fiber. It's nylon and PET. And then the third one is a dedicated nylon material.
Correct.
Oh, and by the way, color-wise, we got black for the composites, as carbon fiber would suggest, I guess. And then the white one, or natural. It's actually natural, right? It's
a natural, yeah. It's a little bit off-white, we say.
There we go, off-white. So very on brand with the millennial culture there. So before I jump into the testing, right? Because I'm going to take you guys into the actual sample testing of each of these parts. I'll allow Thiago to take us down into the rabbit hole of like material science here. Let me know if you guys can see my screen, and I'll be taking you guys, or actually allowing Thiago to take over and take the screen away from me. Here we go.
Good. Yeah. So correct. So first of all, I would like a little bit to introduce what Lehvoss is. So Lehvoss is, we are a compounder, and not many people know what a compounder is. So you can leave in that slide. So a compounder basically is, we take the raw materials available. Yeah. So for example, we have BASF, we have polyamides, we have Arkema, has polyamides, peaks, and so on. And we as a Lehvoss, what we do, we take these materials, we create our own recipe to fulfill a given application. So for example, if you need a conductivity, thermal conductivity, electric conductivity, a more strong material, carbon fibers, and so on, then we will take all this into consideration. Also the way you're gonna produce it. So if it's injection molded, 3D printing, and so on. And then we're gonna give the customer the best option. Yeah. So what this means? It means that, as you can see here in the table, the polymers that we work with is pretty much everything that's available. The only one that we really don't work with is a PVC, because it requires a different technology that we have. And also, if you see the reinforcements in the second part of the table, you see that also here we work with pretty much everything. And then in the additives the same. So this is how we work. Customer comes, we discuss with the customer what is the really need of the application, how it will process, and then we generate a specific recipe. And this is why we have, as you see in the right, 3,000 different recipes that we produce every year. So in the next slide, then we see what are our best, let's say our highlights, as I can say. So we focus really in structural parts, so aluminum replacement, metal replacement. This part that you can see, the white one, is actually the overhead beams of the A320. So it's a holder for the overhead beams of the A320, and it's a metal replacement. Then we have tribology specialization. So when you need materials that need wear resistance, and then you have a chemical resistance, conductivity, electric, thermal, and so on. Important is really that we focus all these characteristics and always keep in mind both the way it's going to be produced. In this case, we show 3D printing, but also we have a lot of recycling in mind. So if we offer compounds that come from recycled, we offer also materials for 3D printing. For example, we have a PET, which is coming 90% from recycled materials. So then in the next slide, we show, so one more, sorry. So here is then what we do. So why LUVOCOM 3F? So what's behind? So here is really when we started the product line, this was 5 years ago. We take first a standard polyamide 6 and we print it. Yeah, so injection molding grade, and then we print it. And this is what we are seeing here, these pictures on the left. They are micro CT. So imagine we printed a small cube, 4 millimeters per 4 millimeters per 4 millimeters, and then we see inside of the material without cutting. And as you can see, when we have close to the heated bed, we have very dense material, very nice. But as soon as we go out, in this case, we didn't have a heated chamber as the method has. So as soon as you go out, then you don't have enough energy. The material starts to not attach to the previous layer, and then it crystallizes very fast. And this is why you have this curve that you see. So you see all these holes inside of the material. And this leaves us with a high porosity. And this was what was always in the mind of a lot of people when they say, FDM, FFF is always porous, it's just not strong, and so on. So what we did is we individualized, we saw that the issue was really this crystallization speed that was too high, and also that the energy, it was not in the material, and we didn't have a lot of machines. So at the time was only the Stratasys, which was very expensive, that had the heated chamber. Nowadays, our life is a little bit easier with the MakerBot. And then we printed again with our technology, and then you can see we reduce the porosity of the material to 2%. And this is very, very similar to injection molding. So you can see in the pictures in the right-hand side that you don't see the layers anymore. So when you break the compound, you have really a dense material. And this is very important to the comparison we're going to do in the next slide.
And I think if I can just stop there
sure.
for a second, because it's something that we hear about a lot, right? People saying, well, what's the benefit of a chamber versus a heated build plate, right? And when you see it as from the outside, you see, both the chamber and the heated build plate can have a fairly flat starting layer, but the actual insides of the parts will perform very differently because of that added material distortion that happens as soon as you start getting even 4 or 5 millimeters away from that heated build plate.
Absolutely. Absolutely right.
For everybody out there who might not be familiar with, mostly, most entry-level printers will have a heated build plate. Just the very first layer is being heated up to guarantee adhesion. But in more advanced systems, like Thiago was mentioning, specifically Stratasys, which is our parent company, they are much more expensive, but they will fill up the full build volume. And that essentially keeps the material happier and allows it to evenly dissipate. That's also true for the method printers. And it's kind of like the biggest differentiator, I would say, on our end.
Absolutely, absolutely. This makes a big, big difference in the end also because, as you're saying, it's not only about porosity, it also comes to stability, so geometrical stability, and also mechanical properties, because when you have a heated chamber, you also increase the crystallinity of the final part.
And that's also one more thing that I wanted to touch on is that we do know that all of these materials, and even the ones that we are not announcing today, as long as they are 1.75 millimeters, you can technically print it with any printer. But even the same material, we will have different results depending on the platform that you're using, correct?
This is absolutely correct. So not only different results, but also different printing speeds, everything will be different. So each system is completely different from the other one. So here then we come to the comparison with injection molding. So what we know about carbon fiber reinforced materials and injection molding. So as you see in the left-hand side of the screen, we have injection molded tensile specimens, and then we injection molded from the arrow. So all the fibers, they are aligned to the pulling direction. Then in the second picture, you see that all the fibers are against the pulling direction. And then in the last one, we injection mold from both sides at the same time. And when we injection mold from both sides at the same time, in the middle, when the two materials get together, we're gonna be a mess with the fibers, but also we're gonna have a weld line. And this weld line will be a defect later. In the 3D printing side, of course, then we can print in a X and Y, so flatten the bed, and then we can align the infill also with the 0 degree, in the 90 degree to be against the pulling force. And in the Z direction, on the results I'm gonna show you, we print actually a cube because it's not so practical to print a tensile because it will bounce like this. So then we print a cube and we cut out the specimen. Yeah. So then in the next slide, I show you the results. And this is, we will check here, we have three materials. Okay, so the first one in the very left-hand side, you can see the solid bars. So the blue solid is injection molded with all the fibers aligned. The red solid bar is injection molded with the 90 degrees. So all the fibers against the pulling direction. And the gray bar solid is the injection molded weld line. Yeah. And then the 3D printed also is the blue is this rayed blue is the 0 degrees, 90 degrees is the red, and the gray also is it's the Z in this case. So here what I wanted to show you is the first thing that we found, and this is very important, is that injection molding also have anisotropy. So you can see that when you test materials in the 0 degree in injection molding and 90, we have a lot of anisotropy. So we have a lot of dropping properties. So this is not exclusive on 3D printing. Yeah, and this is really important.
Let's just also pause for a second, class. I heard this conversation before. Can you speak about what does anisotropy means?
Yes, sorry. So anisotropy and isotropy. So isotropy, it means that a material, it has the same properties from each and every direction you exercise force. So it will always behave the same. And anisotropy means that you're gonna have one or more directions that have different forces. So here's is how we prove this. So if we pull the material with all the fibers in one direction, we have one strength. And in the second one, if you pull in an opposite direction, we have a much lower strength. So this is how it goes. Important to say, injection molding, okay, we have a lot of softwares, mold flow, and so on to predict where the fibers will be not oriented, but it's always a gambling. So as much as you try to predict, not always work. Yeah, and this in the 3D printing doesn't happen because we know exactly where it will be. Yeah,
it's interesting to think about it that way, because also, like, generally speaking, you would expect the 3D printed objects to have a slightly weaker force or strength, but the upside is that you can actually control that strength depending on how you orient that part and have a very specific idea of how it's going to perform.
You know exactly where you have each and every plane and each and every strength. Yeah. So here, important to say also that this material that we are analyzing, the PhT CF9742, it's a 15% carbon fiber material with chopped fibers. Chopped fibers means that we take the fiber, so the carbon fiber, that it comes in a row, and then we cut, and then we put into the material. Yeah. So this shows, in the end, what does it mean? Is that you're gonna have a slightly longer fiber in the filament. Yeah. And then you see that in the middle material, I'm not going to go in much details in this one, but it's the same material as the previous, but instead of 15% carbon fiber, we have 25. But it's the same type of fibers, the same matrix. So you see the behavior is very similar. Yeah. And then we come to the 9891, which is the one that we are talking about today. And here we can see that the injection molding in the 3D printing results, they are very, very, very close. Yeah, so they're exactly the same, so there is no difference. Why is that? Because in this material, we use a little bit of shorter fiber. And when we use the shorter fiber, we reduce this difference between the alignment of the fiber. So when you have injection molding, you have a perfect alignment. 3D printing is not so perfect. And here, because we have the smaller carbon fibers in the material, then we have basically no difference to injection molding. So I think this is really a very differential of this material.
I think that's super useful, especially because we do know that there's a lot of people out there that are prototyping in the 3D printer, but once they know they move into production, they'll 100% be using injection molding. So getting as close as you can to that final state, it's really important too.
Correct. And also here it's important just to say that as you see, the anisotropy here also reduces a lot. So of course we reduce the force of the aligned parts, but this is because the fibers are smaller. But then as a benefit, yeah, then the anisotropy is much smaller.
Yeah.
So then we go to the next slide, and then we talk a little bit. We have only 2 slides more to go, and this is only us talking a little bit about what's PHT and what's the PET. We already spoke a little bit, but basically this product line that we created, this polyamide high temperature, is really when people came to us and they say, oh, we need a polyamide 6, we need a polyamide 6.6, but it's too difficult and so on. And then we tackled really these 2 main issues, which was first moisture. As I said to you before, 4 times less moisture and takes 4 times longer to absorb. So this is also very important. And then also the warping. So before, a lot of people say, you cannot print, it's very difficult. In the method, always is easy because you have the chamber. So then you don't suffer
and
so much.
I promise that we didn't ask Thiago to say this. It was a nice thing to find out that they had an amazing experience.
Exactly. But if you go to open printer, if you just take a standard nylon, it's very, very difficult to print. And here then we make it possible due to the crystallization speeds and so on. And then, as we show in the previous slide, we can go to strengths up to 170 megapascal with 25% carbon fiber, working temperature, as we mentioned before, 150 degrees. And then also we have the 9936, which is the black version of the one we are showing today, the 9825. It's also metal detectable, and it's possible also to contact with the food. So this also will be the next material that we're going to be adding to the MakerBot. So we already started the testing. So awesome. Then soon we're going to have a metal detectable material in food contact. And
allowed. Also, like for all of you guys to know, the idea here is that if it's 1.75 millimeters in diameter, you can use it no matter what. But once it's been approved, tested by us, then we'll give you the more specific temperature settings, print settings, chamber settings to make sure that you have the easiest experience with the material.
Correct. And then we go to the PETCF, and then here, as I said before, main key point is not the PETG, because this makes really a big difference. And as we mentioned before, I think the low water uptake and the excellent surface finish and the easy to print, so as an entry material, I think this is really the main key aspects for this material.
Yeah, I want to, well, I'll take you guys in a minute to the chamber, because that's the actual material that I'm printing with. And you'll be able to see how incredibly flat and smooth the surface is as the printer prints, but I will get to that in a second.
So I think for me, this was what I wanted to share with you guys. Okay. I think we have a couple of more slides with just like a finishing, so there is nothing else. Here is the portfolio. Yeah, of course, guys, if you want to have a look, we have also available on the website, but we have really all the materials from polypropylene to picks and packs, yeah, with carbon fiber, glass fiber, yeah, you name it, we have it. So, and more, we will get more and more materials available to the method as well. Yeah.
Okay. I'll jump back here to start the testing so that you know we can get some questions going as well. And as I said before, if you guys have any questions regarding all of the amount of data that Thiago just shared with us, feel free to post them in the comment section over there. But for now, let me get going with this setup, and I'll come back, as I said before, to showing you guys how is it printing. But I just want to get over the testing first so that we have enough time for the Q&A session. Before, if you guys have joined any one of these in the past, you would know that it's essentially a very quick test, and I have a video of it right now, where we are going to just pull up any one of the samples, in this case, ABS. I have a lot of values already in there available for us. And all that we're doing is using the same sample. It's a bespoke sample, right? It's no ISO specific or technical sample, but it gives us a general reference of the peak load that each of these samples will take. So we'll start with the first material over here, which is a PHT CF 9891. So if you guys can, let me get rid of stop sharing my presentation so you guys can see the full view of the video over here. Load the first sample. And I always get scolded by people saying that I'm not wearing the safety glasses, but I have the safety glasses now. So it's, yeah, sorry about the motion. But yeah, I guess it's a good idea to keep them on. You might not be able to see it. I'll read the values as I'm going through them, and but you will see the main value over here. The machine will record the peak value as we go. So here we go. Sample number 1, 9891, and starting 41, 80, 100, 190, 200, 240, 260. There we go. All right, so sample 1, peak load 270, that's newtons. And by the way, all of these measurements will be in newtons for the time being. Let me just record this, 270. Is that correct? Oh, 269 actually. Give me 1 second. Here we go. 269. All right. Sample number 2. And sometimes it's also useful to see, kind of like what Thiago was mentioning. All of these samples, by the way, I printed them out at 20% infill, but it's useful to see the way that the material fails. So very uneven, which is nice. It essentially means that the load is distributed across the whole model instead of just being like a clean cut, right? And you can actually see some of the fibers. I'll use the macro lens in a second. Let's just finish up the testing first. Resetting here, peak load, and sample number 2, 98, 91, 40, 100, 120, 150, 200, 253. So pretty even, that performance over there, 253. That gives us an average of just around 260 newtons for this first material. Jumping on to the second material, let me just remove this. The fracture is also fairly consistent as well, as you can see, really uneven going across multiple layers. And you can see also, let me bring in the macro lens over here for you guys to see. So you can see the actual infill, really interesting pattern there. But yeah, I just like to look a little bit deeper into the samples every time that we break them. So second material, let's just put this one over here, will be the 9825 nylon. So this is the straight nylon. Let me reset
Felipe,
the read. Yep.
Can you just take the macro lenses off so that people...
Oh, thank you. Yes, good call. There you go. Okay, so this is going to be the nylon, resetting the measurement. And so straight nylon sample number 1. That's 50, 100, 150, 200. Wow. Oh, there we go. But, it's interesting also to see, like, it's a little bit more of a catastrophic fracture, right? It's also 20% infill. But definitely much, I would say it seems to be more brittle than the carbon fiber reinforced one. That makes any sense. So this is 253 for the first sample, 253. Here we go. All right, second sample for the nylon. Resetting over here, 0. And starting 50, 100, 150, a little bit lower, quite a bit lower actually, 185. But similar, I think there's something, I don't know what you can tell us about that, Thiago, but there's something to be said about the consistency of the failure, meaning that the nylon definitely sort of explodes, but both of the samples behave the same way. Whereas the carbon fiber, it's sort of like slowly fractures across the part, right?
Yeah, so this is actually quite interesting. So normally when you have a catastrophic failure, yeah, so that you expect more in the carbon fiber materials, but then probably is due to some of the fibers that are not completely aligned. Yeah, and then you have fibers also in the other directions that gives us this, as you mentioned, that you see some fibers coming out. Yeah, and on the other hand, also in the PA, I don't know, maybe when did you print these specimens, but they seem to be also very dry. Yeah, so this is good. So it gives a lot of strength. Yeah, but then also it's also more brittle. So, for example, if you would put in or leave it outside for a couple of days, you would see that probably your strength would be lower, but you're gonna have more elongation. Yeah, so.
And I think that's also one thing to keep in mind, that it's not only the keeping the material dry, but once you printed the parts out, it will still be, you know, susceptible to changes in humidity and therefore changes the performance of the part.
Correct. This is why normally polyamides, you have two values in the datasheet sometimes. So you have a conditioned value and a dry value. Yeah. So this behavior that we saw from the polyamide, this is really a dry value. So this is really nice.
Yeah. I'll jump into the last test, which is a PET carbon fiber. And yeah, you know, to your point, it's actually still, you know, in the middle of winter here in New York City. So the heating, I think it's actually drying up the environment quite a bit. That might be why I printed this out on Monday, I believe. But anyway, so last run with the PET carbon fiber, so that 9780, sample 1. And we'll see 50, 100, 200, 250, 300, oh fuck, 340, 50. Wow.
There you go.
360. That's impressive.
Yeah, this is good. So this is, I think it really goes back to the point. I think also the PHT before that we tested this, it was absorbed a little bit more moisture. Yeah. The CF. And the PET, of course, it doesn't care about moisture very much. Yeah, so then it really goes. Yeah.
Yeah, 360 newtons. That's a lot.
Yeah.
I'm not sure. I'll have to. I mean, we'll get to that in a second, but I'm not sure we have the rest of the materials usually perform these well. This is crazy. But it's also nice kind of to see the validation of the actual technical values. I think that's why I enjoy this so much, because it's a live testing, right? It can't get any more real than that. All right, so last sample of the PET carbon fiber reinforced. Sample number 2. And here we go. So 50, 100, 150, 200, 300, 350. Wow, 368. So consistently around 360 to 368, 368. That gives us an average of 364-ish, 5. So yeah, and let me go back to my presentation here for a second so that you guys can see. So we got an average of 260, 200, and 340 for each of them. I'll bring them in. Well, I think here we go. So if you can help me with these averages, Tiago.
Yeah.
So if you
we have
the PET.
989, the PET is 364.
Uh-huh.
Then we have 200 in the nylon.
Uh-huh.
And then we have 260 in the PhT CF.
260?
Yep.
Okay. Right. So I'm not populating the graphic right now, but you can immediately see that these 360, that's by far the strongest material that we've tested out. It's even outside of the chart for now.
Yeah.
So really impressive. I'll update the chart, and if anybody wants the actual values, again, this is a very specific measurement with the sample that I designed over here. But the fact that we've been using consistently the same sample, and across different materials gives us a good reference point of the actual performance of these materials. It's impressive that PET almost 100 newtons more than nylon 12 carbon fiber.
Yeah, and this is a very good measurement also. So if you check, so for example, the PHTCF against the polyamide 12 carbon fiber, we are very close. So it kind of validates. Yeah, so it's a similar material. It's not exactly the same, but it's very similar. Yeah. And also when we analyze with nylon, so we have a little bit at 200, as I mentioned to you before. We have this a little bit, I think. Okay, so we have this value that's very close to the nylon, but a little bit more stiff. Yeah. And also this maybe is due to the less moisture absorption and also to the characteristics of the PHT against the normal nylons.
No, I think it's definitely, I'm impressed by it. I wasn't expecting it to be such a big difference.
Felipe, you have a OBS window.
There we go. Sorry, I was just switching over between cameras. But yeah, so that's one other thing. Like, now that we've talked about the specific samples, the tests is kind of complete. Let's talk about like the printing of the materials themselves, and that's why I'm sort of rearranging my camera over here. Starting off with considerations around printing with a heated chamber versus a build plate, and then specific considerations around the print temperature. And I'll start with just my general experience. We got the reference value from Tiago, and we'll be sharing those with you guys. It's going to be available, and it's already available, I believe, on our website. But for the PA carbon fiber, the print temperature is 290. The chamber temperature depends on the support material that you're using. You can use either PVA or SR30. PVA, you can print with 60 degrees Celsius. SR30, it should be printed at around 80 degrees Celsius. Now, what we found out was that increasing the material, the chamber temperature too much can cause some issues when printing. So you're better off with printing at a lower temperature, like 60 for PVA. That's perfect. Actually, that's what I'm using right now. And around 70 or 80 for SR30. I think we will have the final value for you guys to download, because that will definitely affect the extrusion rate in the printer itself, right? Then the second material, the nylon, straight nylon, it's going to print at 270 in the extruder. Again, 60 or 70 on the chamber. I've been using 60 degrees. I have been printing without supports because that makes it a lot easier. And most of the samples that I have right now do not require supports. So 60 degrees, it's like incredibly easy to print for sure. One more thing to consider is, and I'll show you guys this real quick. Let me stop sharing and switch windows. So one thing to consider when you're changing and toggling all of these values, right, is that the value that you slice with might not be exactly the value that's giving out in the in the printer. But for that specific reason, we have the advanced section here in the printer. You can go into sensor info and get the true values that you're printing with. So let me try to get you guys a little bit closer here. A1 and B1 right here stand for the actual extruder heads, right? So I have the target temperature in my extruder, which is 295, but the actual temperature into 290. And that's the value that I want to be printing with, because this is the PET material, right? You have to be conscious about that fact. As soon as you start like getting into a more specific type of material, you want to really make sure not only to change the values when you slice the material, but also make sure that it's actually being reflected in the printer. And the printer is really smart. It has a lot of sensors for you guys to play with, even the humidity sensor, which I really appreciate, especially because of this kind of conversation, right? You can see I can measure out the humidity values, in this case, 15% and 20% for each of the material base. So that gives me a lot of knowledge to know how the material is performing, how the printer is performing, and just to adjust accordingly. Because as I said, this material, the PET, you want to print at 290 degrees in the nozzle, but that meant for me at least that I had to slice at 295, and then the actual effective temperature that I was printing with is 290, right? The current temperature 290, target 295. So it's a really high temperature in any case, which is why you want to reach a little bit higher and then sort of stabilizes at the desired temperature.
Correct, and this is important because these 5 degrees, they may not seem too much, but these, in the terms of rheology of the material, it can mean that maybe the printer can clog or something, but it's really because you need the energy, so then the material can flow outside of the nozzle.
Yeah, and so real quick, so as I said, I wanted to see, for you guys to see the flatness of these parts. It's like really, really smooth, right? This particular part I'm printing an electronics cover. It's really flat, really smooth. I'm hoping that the camera is actually being able to focus appropriately. But definitely, impressively straightforward after really getting those values in. And that's kind of the benefit of having the materials run through us, because we will spare you that sort of testing process and just give you, these are the exact settings that you need to use. The cool thing about the Labs platform is that you can print with any material. It doesn't have to be validated by us, but the ones that are, such as this, will come with the benefit of actually having, that, the knowledge on how to print and the implications and whatnot. So just to round things up and starting, to get into the Q&A session, right? So as I said, so far, impressed to say that we just tested our best performing materials, at least strength-wise. Impressive. I'll be printing with it quite a bit from now on, for sure. Again, 30 materials available for you guys to choose from. And yeah, with that, I think I'll open the floor to a Q&A and allow also, I think that Alejandra in the back end, she has some both questions and a poll for us to go through. But yeah, for now, it's, thank you so much, Tiago, for sure, for coming and joining us. So let's start with
really my pleasure.
All right.
Okay, thank you, Felipe. We are ready for questions. We definitely have plenty. So let's get started. Which materials are more consistent in terms of performance across humidity levels?
Yeah, so then when we speak about the 3 materials that we present today, absolutely no doubt is the PET. Yeah, so the PET is really much more much less moisture sensitive.
What would be the downside of printing with PET? Because we've talked about it, like right now, it seems like it's a magical material. It does it all. It's not moisture sensitive. It's also super strong. What's the downside of it?
No, I think the main downside, it's just that the mechanical properties, as today, okay, in your tests, we saw that we have a quite good result. But then when we have impaired conditions, so for example, the PA dried and the PET also in neat conditions, then we will see that the mechanicals of the PA are a little bit higher. But apart from that, there is not really a big downside. It's just a material that is very well used in the medical industry. For equipment, so cases and things like this. But all the people always relate it to bottles. So this is just a feeling.
Okay, and keeping it in the moisture section, what indication shows that a filament has too much moisture content?
I can answer from the side of the printer. Like one of the first things that you will see when you're printing is that it can start to sputter, right? So from time to time, if it has really small water bubbles inside of the material, as it prints, the material will sort of like sputter a little bit. You can also hear the extruder hissing a little bit. All in all, 2 things to consider on the method is, well, for the method materials, you can keep them and you should keep them inside of the material base, because as I said, not only do we have the sensors to check on the filament, the actual sensor to check on the humidity levels for the material, but also it's completely sealed, right? And then the second thing to note, which is also one thing that I had talked to Tiago about, is the fact that the printer is able to anneal the material. So even if you find out whether it's, your extruder is oozing, your prints are failing a little bit, you can always put the material inside of the printer, just like what the suggestion of putting the desiccant in the microwave. There is a function and method to dry up the material, and you can actually, you recommended that to us, Tiago, to run the function when you first get the material, and it essentially heats up the chamber to, I think, around 40 degrees Celsius. So it's not a lot, but it's enough to get rid of most of the moisture content.
Yeah, this is really a good point, and I think the other indication that you're gonna see very easily is when you have when your head will travel, and then you see a lot of oozing. Yeah, so the popping sound and the oozing, these are really things that if you see oozing, please dry the material.
Mm.
Okay, next question. What support material is necessary for each of these materials?
That's actually one of the benefits. You can use either one. You can use PBA. Well, actually, technically, it's three options. You can use breakaway, which will print on the same material, and then you just remove it by hand. It's a little bit trickier for more complex geometries or things that have a lot of holes in it, because then it can be harder for you to get in. You can print with PDA, which is water soluble. But one thing to consider with water soluble is that if the material itself is sensitive to humidity, then you're soaking in water, you're actually challenging the performance. And you can also print with SR30, which is also soluble. So both materials are an option, or the breakaway if you're not, if it's a more straightforward geometry.
And what extruders are these materials compatible with?
Can you say that again? Sorry, the materials?
What extruders?
Oh, right. So all of these materials will be printing in the labs extruder. It's one of these guys. As I keep saying, like this particular extruder allows you to print with any third-party filament. Me personally, I have a few of these extruders. The reason is because you really want to have dedicated extruders, at least for material families. For example, I have one extruder just for metal 3D printing. I have one extruder for composites, and I have one extruder for polymers. Because generally speaking, they will have similar print temperatures. If you are printing with something that prints at 200 degrees and then you move up to 290, like the PET, you can have some issues because the leftover material will start to collect and prevent you from having the best experience. But all in all, it's a labs extruder, allows you to print with any material, any third-party material on the method.
Great, good to know. Yeah, because I have a question from somebody that is interested. Tiago, you had a very full list of all the materials, and this person is interested in PEEK and was asking if it's compatible with our method platform.
You can go ahead.
That's... yeah, no, so PEEK is so PEEKs and PECs and PEIs. These are materials that really require a very high temperature. I think MakerBot and the team are working on it. We
I didn't
already
say that. So
yeah.
No,
I think
definitely it's a super interesting material, really high temperature for sure currently. So the answer is right now, PEEK is not compatible with method. The limit of the method right now, it's around 300 degrees for the extruder. That's just, right on or above the PET printing temperature. The chamber temperature will go to 110 degrees. So it's definitely, well prepared. But for now, the answer is no. PEEK is not compatible with method right now. So that's the other thing to consider, right? The filament needs to come in 1.75 diameter in the spool and be able to print in at or below 300 degrees Celsius.
And this allows a lot of materials already.
Yeah, you saw it. I mean, 300 newtons for something this small. The cross section is like 1 centimeter. No,
yeah,
like 5 millimeters square probably. So yeah.
Okay, the next question. Does Method X pre-populate the necessary settings for use, or must it be done manually?
It does, as long as you're using a method material, meaning a MakerBot material, sorry. So when you, and actually I can show that to you guys if you want to see. I'll move over my screen. I was showing the printing process, but I'll go back to the material section here in the printer, and you'll see. So when I'm printing with labs, I'm hoping, and you can let me know, Tiago, if this is like properly.
It's
okay.
focused. Yep.
So when I got the materials here, right? Since I'm using the labs material, it doesn't detect which material I'm loading because I'm using the side loader of the printer. But for the support material that I have here underneath, if I remove it, you'll see how, sorry, it immediately stops detecting the material, right? And it goes to blank because it doesn't detect the material. Each of our materials spools comes with an RFID tag. As soon as I drop the material in, it detects like it's PBA, it's natural. And it's not only useful for the printer, but also useful for the slicing. So in our slicing software, you'll be able to immediately detect that through the printer and essentially prepare the slicing software to actually have the right setup to print with that material.
Thank you, Felipe. Now that we're talking about method, does method require a routine maintenance, maybe a fan replacement, air filter, etc.?
I wouldn't. Well, I mean, of course, it is a machine, right? So you want to keep a look at it. So far, mainly speaking, it's the extruders, right? The extruders will have a life of about 6 months, depending on how much you print with them. We do have air filters on the top, and I can open my shot a little bit here. So above my printer, I have the clean air station. So that's actually a HEPA filter and a carbon filter on top of the method. Those, I think they'll last for about 10,000 hours, and then the printer will ask for you to replace them. But overall, no, not the fans. I have had my machine for about 3 years now, and the fans are running just smoothly. The gantry is perfect. The bays are perfect. It's mostly the extruders, and then it all depends on how much you're printing with them.
Okay, next question. Sometimes when printing small features, like a few millimeters in size, I've seen the support material come loose from the model. Why is this happening?
Well, overall, I would say that it depends on the type of feature that you're printing with. If you're thinking about printing, minifigures or something that's very delicate, FDM will definitely will struggle with anything that has a cross section of less than, let's keep it safe at 5 millimeters, right? Down below 5 millimeters, it gets tricky really fast. So yeah, I would say practice the part orientation. That will probably help a lot. And then sometimes breakaway material can be a little bit more stable with those finer sections, just because it's the same material adhering to itself. It's going to have a natural tendency to do so. And that would be my general recommendation. Either test out the part orientation or use breakaway supports instead for those fine elements. But just consider that, right? These type of FDM printers are better suited for the tool heads, the jigs, the fixtures, something that's a little bit more robust. Like this particular example, I got the gripper over here. So very tiny details. You probably would need a laser SLS printer, depending on it depends a lot on the application. So mixed answer, either changing the part orientation, using breakaway supports, or if you're trying to print something very fine and tiny, right? Kind of like think about jewelry or little toys, you're probably better off with an SLS.
Thank you, Felipe. Now that you were touching on part orientation, I have a question. Can you print a different orientation on a different layer by printing 90 degrees to the previous layer?
Well, you're always going to be printing 90 degrees from the previous layer. I understand the question. So the answer is you can change the infill settings for sure. You cannot do that on a layer by layer basis. The easiest change is going to be to print either with a solid infill, kind of like what Thiago was describing, where you completely fill up the internal space of the part, or changes on the infill pattern. You can have hexagons, you can have triangles. We even have some fun ones like donut shape. They don't really have a mechanical application. It was just for fun, but you can do that, right? Vertically, it's not going to do. And I saw somebody asking about the not printing in a non-planar fashion. That's not possible with this type of gantry, right? We are printing in a layer by layer orientation, and the main change is going to be either solid or different infill patterns.
Okay, great. And as last question, first, where can our audience buy these materials? And also, Felipe, can you just explain how many different method models we currently have, and if there's like a promo or discount going on?
Right. I'll let you, Thiago,
Yeah, so for the materials, you are welcome to visit our website. Over there, we have the links to web shops of our partners that they can directly sell to you 1, 2, 3, 5, 10, 100 spools. We are here to have it.
So yeah, and we can always share that link for the method configuration. So we have 3 of them. We have the Method X, which is what I've got here, and then the Method X carbon fiber. The carbon fiber actually comes with an additional extruder, the 1C, which allows you to print with our dedicated carbon fiber materials, nylon 6 and nylon 12. All of these, the 3 versions, so Method X, and Method X carbon fiber, will be able to print with the labs extruder, and in particular with these 3 materials that we introduced today. So the nylon carbon fiber, and the PET carbon fiber. Yep. So, and regarding the promo, I think you have better information on that, Andrea, but yeah, we do have a promotion running right now. I would strongly encourage you guys to go check that pricing on the site. But if I'm not mistaken, we were doing the free extruder, but I don't know if I'm correct on that one anymore, Alejandra. I think she's checking on that promo, but yeah. So the three printers, I think that generally speaking, I would default to the Method X to get going if you're interested in a wider variety of materials, just because the Method X does have a difference in the hardware components. It will be able to go to a higher chamber temperature, which is really useful when printing some more, demanding materials like ABS, for example. You really need to go to 90 degrees at least in the chamber for it to be printing successfully. Method X is definitely a straightforward one, kind of our workhorse, sorry, the regular method, but it will be limited to 60 degrees Celsius in the chamber, right? So if you need to print with anything that has a requirement of over 60 degrees, you need the Method X. And the Method X carbon fiber, the big plus is that it comes with an additional extruder that allows you to print with our composites, dedicated composite materials.
Well, thank you so much. We'll make sure to add the current promotion to the thank you email that everybody will receive tomorrow alongside with the recording of this presentation. But thank you very much, Felipe and Thiago, for this incredible material showdown.
Yeah, no, thank you. It was a lot of fun. It's always nice to break stuff with somebody.
No, it was really, really nice. I enjoyed so much, and really thank you very much for having me on the show. It was a lot of fun, and I'm looking forward to the next materials.
All right, thank you. Have a good one, everybody, and we'll talk next time. Thanks.
Thanks, bye.